Okay, so let's get started. A few quick announcements. The Geographic Information Systems tutorial is going to be released hopefully tomorrow, definitely this week at some point. Please resubmit. So for those that whose topic was not accepted in the tutorial proposal, resubmit by today just so we can confirm that you have a topic. That will in fact work. I think people, if I was going to have more office hours today to talk with people that didn't have a topic, but for the most part, I think people were fine, or if they did have a question, they just picked another topic. So I wasn't going to have scheduled office hours anymore to handle that. But let me know if you would just send me an email if you do want to talk about that. I know I have a few outstanding, but I'll reply to those this afternoon. Homework 3 due next Wednesday, back to normal schedules. I think in retrospect, it was probably a bad idea to give everyone free late days, which effectively just meant you had no late days. This is a longer deadline. I wouldn't do it again. I think it just kind of psychologically makes things a little tougher. So hopefully everyone got through that okay. We're going to post the distributions for Homework 2 later this week, I think, on Piazza. But Homework 3 will be due next Wednesday as normal. One last thing, well, two last things. The final exam dates have been posted. And if you remember, that we don't have a final exam or a midterm exam, but we are going to have a presentation presenting short videos from the work to the whole class. And so we're going to have a final exam, and we were going to do it that date. Now, as soon as this was posted, I got about 10 emails from people saying that that's really late in the final period and they want to go home by then. But in general, those are the dates of the finals, so we are asking everyone to do that. If we try to reschedule it, then it automatically will cause conflicts with other exams, so it's kind of tough for us to do that. If you do have a definite conflict, please do email me. They are videos, so you can potentially record them beforehand, but we really want to have as many people there as possible. So that we can all actually participate in the viewing of these things. So that's during those 3 hours we'll be having those presentations. And finally, there's been a few people that are posting code to Piazza still. So if you post code from your assignment, please make it a private post. Don't make it a public post. If it's code from your actual answer, if it's just general code that from the lecture or anything like that, then you can certainly do it. But if it's code from the assignment, from your answer to your assignment, please do make that a private post. Okay, so we're going to pick up today. Today we're mainly going to talk about classification, but we're going to pick up first, finishing off regression. And I was a little bit late getting up the slides this morning. They are up now on the website, but I changed one thing in this presentation that I think it makes more sense to include it now, and so you can let me know if it actually makes sense here or not. Anyway, last time when we finished, we derived sort of derived at least, most of the way derived, the solution to the least squares problem, right? So this is the machine learning algorithm that has a squared loss function, a linear hypothesis class, and optimizes it by setting derivatives or gradients equal to 0. Right? And when we do all that, we can actually solve the optimal parameters in a nice closed form. And the solution is just given by x transpose x inverse, x transpose y. And those are so common, in fact, they have their own name. They're called the normal equations. So it's a very, very sort of standard and common set of technique, or very standard and common technique. And the nice thing here is that this, unlike our sort of term-by-term notation, this will work for any number of features. So if you have 100 inputs, you just form your matrix, you form these equations, and you'll get your answer. So very nice, compact, expressible in less than 10 characters, as is written in math. So let's take an example of this, about how we do this. So I'm now going to go back to our example, and all this code is on the website. But I'm going to go back to our example of predicting the peak energy demand given high temperature, or actually given whatever we want to be given. We can add whatever features we want to this problem. But in this case, we're going to have two input features plus a constant feature. Remember, we wrap in that constant intercept term along with the feature. So we include a feature that's always equal to 1 across all our data. And we solve it. We solve for theta equals x transpose x. Remember, x, the big matrix X, is a matrix where each xi is a row of that matrix. So we set up this matrix, we solve these equations, and we get out some solution. And what this says is the coefficient on predicted peak demand for temperature is 0.046. So you're going to predict 0.046 times the high temperature for that day, plus 0.027 times a flag of whether or not it's a weekday. So it's 0 if it is a weekday, 0 if it's not a weekday, 1 if it is a weekday, and then you subtract off 1.683. So that's our new formula. It has two features now that tries to predict what the peak demand is going to be. And it's harder to plot this now because now we actually have the two-dimensional input space. So I could plot it as like a 3D plot, but I don't want to do that actually for the same reasons that I don't like 3D visualizations unless you can really interact with them. They're just hard to see. So what I'm doing here is I'm plotting two different cases. I'm plotting the case for it being a weekday. So here I subsetted all my weekdays and plotted what that line looks like when the isWeekday feature is set to be equal to 1. And here I plotted all the weekends and plotted what this line looks like when that isWeekday feature is set to be equal to 0. And as you can see from both the math and from the figures here, the effect of it being a weekday is to bump up your prediction about what we expect our consumption to be, because people tend to consume more electricity on the weekdays. A lot more offices are open. They tend to use a lot of air conditioning and that kind of stuff. All right, any questions on this? OK, so before we move on to classification then, I want to talk about two more things actually. But the next thing I want to talk about is a different way of solving these optimization problems. So remember, we sort of said that our canonical problem that we always want to solve for machine learning, I have to go back a little while, is this problem. We're minimizing our parameters, the sum of losses between our hypothesis, our prediction, and the actual true label or true output in our data set. Okay. And one way we can solve that problem, find the minimum value, the value of theta that minimizes that, is by setting derivatives equal to 0. But another way we can do it is a different method called gradient descent. Now, gradient descent takes advantage of the following thing. It is true that the condition for certain smooth functions, the condition for them to be at their optimum is that the gradient has to be equal to 0. But the gradient actually also provides a lot more information than just that. The gradient also points in the steepest uphill direction of the function. So I actually want to clarify what I mean by that a little bit. So we know kind of from 1D calculus that the gradient is the slope of a function, right? So if we evaluate the derivative, rather, is the slope of function. So if we evaluate the derivative there, we're going to have a positive number sloping upward, right? Indicating an upward slope. It takes a while to go up. OK. For a 1D function, the derivative indicates the slope of the function. In other words, the derivative points in an uphill direction for that function. Right? Similarly, if you're on this side, the gradient's this way, it's negative, so it's pointing again in an uphill direction. Right? So the gradient always points kind of uphill. Now the nice thing is that this actually generalizes to higher dimensions too. So what I'm showing in this plot is a two-dimensional function, and I'm showing what are called the level sets of this function. What that means is that, the function, you can think of it kind of as, well, I'll draw another one here. It's a little different from that. But you can think of a function as like being bowl-shaped. These would be the lines of equal value of that function. So the function is at its minimum there and kind of is curving outward like this. That's the drawing I'm drawing right there. Okay. So it's, a representation of a 3D function or a 2D function with two inputs and one output. But I'm just showing what are called the level sets. And the gradient for this function captures derivatives in both dimensions. Right? The gradient contains the derivative in the first dimension and the second dimension. And what this does, this is actually a vector that points in the steepest uphill direction at any point of the function. So it's kind of like we can look all around, any point in the function, you can look 360 degrees around you and figure out which is the steepest direction uphill, but you don't have to actually test all those values. You can just compute the gradient, and that gives you the uphill direction. And this is very nice because this lets us, and that generalizes to actually however many dimensions you have, it's still the direction pointing upward. So what's nice about this is now we can have very high dimensional functions, and we know a direction that moves us higher in the function. And of course, we don't want to make the function bigger. We want to make the function smaller, right? So what we're going to do is we're going to take steps in the direction of the negative gradient. We're going to take the gradient and subtract some multiple of the gradient from our current set of parameters. And in fact, what we're basically going to do, so if theta is here initially, then we know that theta minus some small constant times the gradient. We know that for at least some small step size, that's going to have a lower function value than the current point, right? You can't go too far, because if you go too far, this is the negative gradient direction. So if you go too far, you're going to step over there somewhere. But for small enough steps, you're going to be guaranteed to make some progress there. And that's the idea of this algorithm called gradient descent. So the gradient descent algorithm is very simple, actually. And I'll describe now kind of how this applies to minimizing a general machine learning optimization problem. Remember, the function we're trying to optimize, I probably should write it again, is minimize over theta, the sum from I equals 1 to m. M's the number of training examples we have, of the loss between our hypothesis and the true output. And so all I'm going to do kind of in very general terms here is compute the gradient of this function, because this is the function here that we're trying to optimize. And the gradient of the thing is just exactly this. I mean, all actually I'm doing here is I'm just pushing the gradient within the sum. So because the sum of the gradients is equal to the gradient of the sums, you can just move it within the sum. But in general, the way a gradient descent algorithm will work for machine learning is you start by initializing theta to be actually it could be anything for the right kind of functions, but 0 is a common one. You can't actually always use 0, depending on the function you're optimizing. But 0 is a good one, at least for the first half of the class until we get to neural networks. So 0 is a good starting point here. We can compute the gradient then, and the gradient here is just going to be the sum of the gradients with respect to the parameters of each loss function, right? That's sort of the generic gradient of this whole term here. And then we update the parameters, theta to be equal to theta minus some small, what's called a step size, times the gradient. Right? And this algorithm, as simple as it is actually the workhorse that drives almost all machine learning in practice these days. There's actually one slight difference that you actually don't take the gradient with respect to all the examples. You only use some of the examples at a time, and you iterate over them. But we'll get to that when we talk about larger scale learning. But this is really the workhorse of machine learning. It's just this algorithm here. There are some tweaks. You add like momentum terms that kind of keep you from bouncing around too much, but those are all details. This is just the algorithm right here. It's a question. What's alpha? Yeah, so the question is, what is alpha? So alpha is what's called a step size. So it's an input to the algorithm. And I'm saying almost nothing about how you choose what alpha is here. The idea is that if you take a small alpha, then you're going to make some progress in your function, right? For small enough, we sort of know by some continuity assumptions that we're going to make some progress in our function. Actually, it doesn't hold if the function is not smooth, but for smooth functions, you make progress. If you take too big, but if you take too small an alpha, you kind of make very, very slow progress. I should actually probably include a plot on this. I don't have a plot on this thing. I have a plot only for one alpha. But if you take too small an alpha, you're going to make progress that's too slow, right? You're going to take a lot of iterations. It's not going to make progress. If you make one that's too big, you're going to start bouncing around. You're not actually going to reach the optimum, right? So there's a trade-off somewhere, and that trade-off is completely unknown before you actually start trying to optimize this thing. There's no real reason why you should know beforehand what this alpha should be. There are ways to do a line search to determine what it should be as you're searching through, as you're optimizing the function. But actually in machine learning, it's more common to normalize our function in certain ways and then kind of pick a few values of alpha and have that be that. Is the most common way people actually do. Yeah. So the question here is, what if it leads to a local optima? And there are two answers to that. The first answer is that for the whole first class of functions I'm talking about in this first portion of the class, that's not a concern. So for example, the least squares objective is what's called a convex function, which does not have local optima. This doesn't really matter. We're not really going to worry about this too much for the sake of this course. But for this algorithm and for all the ones I'm going to talk about next time, there are no local optima in this function. Or rather, more speaking, every local optima is also the global optima, or a global optima, if it's not unique. So this is not a problem. Now, the second answer is, even when there are local optima, it still doesn't seem to be a problem. So neural networks have tons of local optima, and it doesn't seem to actually affect these algorithms. They don't actually seem to be that badly affected by them. It still seems to work really well. So we're going to completely ignore the problem of local optima for this course. Yeah?
What if you have some three-dimensional space and you're at the top of like a hill?
Yeah.
And no matter which direction you descend in, it's like the same rate of descent. So like, which direction will the gradient descend?
Well, so, okay, the question is, if this is sort of inverted and you're at the top of this hill, instead of in the bottom of a bowl, which way will you go? Well, actually, if you're exactly at the top of that hill, you won't go anywhere, because exactly at the top of the hill, the gradient's also 0, and so you won't go anywhere. You will not make an update. If you're just slightly off, though, well, now all of a sudden you do have a direction, and you'll go that direction. So that's just how it determines it. Those problems don't occur in practice because being exactly at the top of the hill is very difficult. Now, there is a problem with things that kind of look like hills or look like what are called saddle points that are difficult sometimes for these things to escape. This is actually well beyond what we actually are going to worry about here, but just if you're curious, the problem of saddle points is a very real problem in optimization, and essentially what a lot of these modifications, very slight modifications of gradient descent do, is they help the optimizer escape saddle points better. But in general, it's very hard to know what you do with just gradient information in those cases. But the top of the hill case is very unlikely, and it's not really a problem in practice. A saddle point is where you're at a minimum in some dimensions and a maximum in other dimensions. And that actually can be tricky sometimes, but it isn't that bad. Again, that's not relevant. So if that didn't make any sense, then please don't worry. But just extra information. Okay, so let's look at this. Let's see what this looks like for least squares now. So least squares, we know what the gradient is, right? So the gradient, we actually wrote it a few slides ago. The gradient of least squares objective is just this thing. So that's what we subtract from our parameters. So our update, oops, I forgot the, actually no, okay. I guess you could just combine this into one slide and it wouldn't really matter. But the gradient here is just equal to the gradient of least squares objective, and then we'd perform our gradient descent update. You could make this one line. There's no point in it being 2 lines, frankly, but trying to remain consistent with the previous slide. In fact, you really could capture everything you wanted about gradient descent for least squares by just the one line. Theta is equal to theta minus alpha times the gradient. That would tell you everything you need to know. And you repeat this, and in theory, you should repeat it until you meet some termination condition. But the reality is, what people don't really do is they just repeat it until their objective seems low enough, and they stop. Or maybe you want to, care about some error you're trying to optimize on some other set, and you optimize until that seems good enough. So here's what this looks like for least squares. There's one little thing I'm actually doing here, which I'll get to next, in addition to just running gradient descent here. But if I start out with theta equals 0, my cost is quite high. It's like 1,400. Again, that is just, the number there is kind of arbitrary. It is just that on this peak power prediction data set, if I predict all zeros everywhere, if my theta is 0, I'm going to make 0 predictions for everything, right? Because I'm just going to predict theta transpose x, which is always going to be equal to 0. And that has a certain error, right? So as I start moving that, though, I start quickly having a lower sum of squared errors between my predictions and my actual, until pretty quickly, and it's actually fairly fast, it takes about, in this case, about 20 iterations, that I converge to the same value I get as if I run the least squares solution. So if I compute x transpose x inverse, x transpose y, versus continually updating the parameters based on this gradient, I, of course, converge to the same solution. This is one case where there is no local optima, so we're going to get the same solution here. And it just takes me this many iterations. Now, the question of which one is better actually has a lot to do with how expensive each iteration is, because solving it exactly will immediately give you the right solution, but at the cost of computing a matrix inverse. Now, we're not going to get too much into this, but for those that sort of care about this, the cost of a matrix inverse is cubic in the number of dimensions of the matrix. So in this case, that's n. So when you have a lot of features, it typically can be better to do gradient descent than it is to do the direct solution. It just ends up working faster in practice. And that's sort of the reason why this is a sort of a workhorse for machine learning. The other reason is that least squares is about the only case where you actually do have a closed form solution that you can get the parameters immediately. In almost every other case, you have to do something like this. Yeah. Okay, the question is, are the matrices always invertible? No. So we're not going to worry about that. We'll talk about that more when we talk about regularization later. For now, assume it's invertible. And if it's not, it's just numerically unstable, so you can add a little bit of regularization anyway, which I'll mention in a second, and everything's fine. Okay, so a couple last things. The first thing remember when I started out, I sort of said we're going to use the squared error as our loss function. This is our loss function to measure how far off we are from our predictions. And this is fine, but why did we pick squared error, right? Well, I think you can justify it in a few ways, but the reality, I think, is that we picked it because it's kind of easy to optimize. We picked it because you can give an exact solution. And an alternative, for example, would be to use the absolute error. So the absolute difference between our prediction, remember, x times theta is our whole vector of predictions here. But really what we're doing here is we could take the sum of the absolute value of theta transpose xi minus yi. And instead of squaring that, we just take the absolute value. Right? That would be very reasonable as a loss function too. It's also always positive. It gets bigger as you get farther away from them being those two things being the same, and it's 0 when they are in fact the same. So it seems pretty reasonable, right? This has a lot of names actually. This goes by the name least absolute deviations. It's also called robust regression, which I'll kind of allude to why that's the case a little bit in the next slide. But there's a few differences now. So the first difference is that unlike least squares, in this case, we no longer actually have an analytical solution to this problem. There's no sort of matrix inverse or matrix equation we can write that gives us the optimal theta here. And so we have to resort to algorithms like gradient descent. Now, one sort of technical point is that this function actually is not even differentiable because this absolute loss function at the 0 point has a point where it's not differentiable. So what we're doing actually is not technically gradient descent. It's called subgradient descent because this is, even though it doesn't have a gradient, you can kind of think of this thing, even though it's not technically a gradient of that function, it's what's called a subgradient. So you end up having something very similar to a gradient, and we're going to completely ignore the differences between these for this class. So we'll still call it gradient descent, even though technically it's subgradient descent. And that's very common, actually, I should say, even in machine learning these days. People don't bother oftentimes saying subgradient descent when they just mean the same thing. And the key part here is that with a little bit, and I should say, I'll use this other notation of the norm, what's called the L1 norm. So that just means the sum of the absolute values of this vector. This is called the L1 norm for those that might care about this. And it's just a sort of a more convenient way of writing it than writing the sum. Yeah?
Always mix up the L1 and L2 norms. Should I worry about learning about that?
So the question was, if you mix up the L1 and L2 norms, yes, you should probably not mix those up. The L2 norm is the sum, well, the L2 norm squared is the sum of squared elements of a vector, and the L1 norm is the sum of absolute values of the elements of the vector. And they're actually somewhat different in what they measure.
So L1 norm, you take absolute value of each element.
Each element, they add them up.
L2 is square each element, sum them. That's where
The L2 norm is actually sum them up, square them, sum them up, and take the square root of that whole thing. But the L2 norm squared, which is what we were using before, is you don't take the square root. And it turns out, though I won't go into it, the gradient or subgradient, technically, of this thing is just x transpose times the sign of this, where this is, again, still a vector. So sign of a vector just means we replace every element of that vector with its sign. So if it's positive, we replace it with +1. If it's negative, -1. And the reason for this, by the way, is just because the derivative of this function here, in this whole range here, right, the derivative is always +1. In this whole range, the derivative is always -1. So that's equal to the sign of the value here. And by the exact same sort of chain rule and other rules that we had before, you get this expression for the gradient. Or subgradient, which I'll say here, but probably stop saying pretty soon. Okay, so let's see how this looks now. So this is, I know, less impressive than you might think. But what I'm showing here is the least squares solution. So the squared loss, the theta that minimizes the squared loss. Again, what I'm showing here really is I solve for the optimal parameters of the squared loss, and then I plug in that function to make to draw the line corresponding to that function. I do that once for my parameters that I get out of the squared loss, and once for my parameters I get when I minimize the absolute loss, sum of absolute losses. And they look pretty similar, but they are different, actually. And it's actually important how they are different, too. So the absolute loss fit is slightly, ever so slightly steeper. Right? So it's a little bit above the line over there, and though you can't quite see it, it's a little bit below the line here. Now, the reason for that is a property of the absolute loss, which sometimes is called a robustness property. So if you think about the penalty you suffer for making a wrong prediction, if you make a wrong prediction that's very far off in the sense of the squared norm, right? So it's sort of you have some term where theta transpose xi minus yi. You have some term where this is fairly large, right? Well, when this is big, and again, I'm being a sort of a little bit vague when I say big, but when it's a large value, then the squared value of this is going to be a lot bigger than the absolute value. This is only for big differences here. When it's big. Right? Actually, the opposite is true when it's small. When it's small, small squared is much smaller than absolute value of small. Right? So what this means in practice is that what the squared norm will try, what minimizing the squared error will try to do is it will put a lot of effective weight. You're suffering a lot of your total loss from those examples that you're getting wrong the most, that you're making the biggest errors on. Right? So in particular, in this case, this one right here, you can't actually even see what the function is, but you can extend the line here. This one here, we're making the biggest prediction error on. Right? So this point here is pretty far off from either of these two lines. Now, in the case of the squared loss, that's going to cause us to suffer a lot of penalty in our objective function. Whereas in the case of the absolute loss, it isn't as big a deal. Okay? So, and in fact, we could have one point even further off that is way, way up. And if we had this point, was maybe replace it with that that legend point up there, that would cause a really big loss for the squared error function and probably shift the entire function up so that we were doing better on that one example, right? So we paid less, we sort of had less, we were penalized less by that one example. In contrast, the absolute loss doesn't really matter, right? Because we actually pay the same penalty for this as just, if you stack this up many times and you look at that. So we probably pay the same penalty for these 5 or 6 elements here as we do for this one. And what that means is that and again, this has been sort of a roundabout way to say this, but the absolute loss is what's called more robust to outliers. So you can have a few points that are big outliers, and it tends to be less affected by that. Whereas minimizing a squared error, if you do that, you will be heavily affected by outliers, and it will largely affect your final solution. And I'm sticking with real data here. This is not just made up to emphasize that point. This is actually all real data. But even on this real data, you can see those effects, albeit in a minor way. That's all I'm going to say the difference for now. The reality is, in a lot of cases, these end up performing similarly. But there are some key differences, especially when you do have things like large outliers. Any questions there? OK, so one more thing before we move on to code, and then before we move on to classification. So I'm going to mention this term here, not because it's actually best fits in here, but just because it ends up being important to how these algorithms actually work in practice. And so I want to at least mention what I mean by this term here. So I want to mention the term regularization. And what I mean by that is, oftentimes, I've said that this is our canonical machine learning problem. But oftentimes, we actually want to solve something a little bit different. There are many cases in which this term here, we can effectively start making very small differences in that term, decrease the loss by a tiny, tiny amount by making our parameters huge, right? So we'll get much more to this later when we talk about overfitting and we talk about nonlinear regression. But just for now, I'm just going to put it out there that we often want to actually trade off minimizing loss with keeping some notion of of smallness for the parameters themselves. So we're actually minimizing some combination between our loss, our sum of losses, and what's called a regularization term, which is usually some norm of the parameters themselves, right? Now, again, I keep saying this, but we'll get to this much more next time. The only thing I want to emphasize for now is that this is actually the canonical machine learning problem. You can use different norms here, by the way, too. So the L1 norm, for example, is very common. It's actually has some very nice properties, but we're going to focus really on L2, the L2 norm squared there. Which again is just the sum of the squared entries of theta I. So if theta I has very big values, we'll pay a heavy penalty here. If theta I is all 0, we don't have any cost here, but we probably don't have a very good predictor either. So we actually are thinking about balancing these two things. Now the one thing I'll say to this now is that when we do this, when we add this, and we'll talk about why we want to add it a lot more, but when we add it for something like linear regression, we are effectively penalizing the parameters equally. So we're saying, a big weight on feature 1 costs us the same as a big weight on feature 2. And that does not make sense if the features themselves are very differently scaled. So let's go back to our example here. We have temperature. Temperature varies between 60 and 100 degrees in this case, degrees Fahrenheit. But those are the values we have in our matrix, right? 60 to 100. And so the effective scaling of the parameter that multiplies that is very different from the scaling that, say, would multiply the is-weekday feature, right? Because the is-weekday feature varies from 0 to 1. It's a much smaller range, so you're going to need a much bigger weight on that to capture the same sort of differences in the output, right? And in fact, we see that. So we looked at our actual solution here. We had a much larger value of our parameter for the second entry here than for the first one, because the first one really varies a whole lot, right? I mean, you don't need a very high slope here to get a pretty big increase when you talk about looking at this value than the second value, right? The is weekday, and so especially when you add regularization, though also actually just for things like gradient descent for the sort of stability of the algorithm, you often want to rescale your features to be on a similar scale. Okay, so we will talk a lot more about data preparation as well, and this is one step of data preparation. But for now, all I will say is that it's very common to perform some sort of normalization on your features before you run the algorithm, right? Because we can always, the actual numerical value of these things isn't that important, right? You can scale temperatures by 10, and you get the exact same looking plot, right? The function should be in some sense the same. It's just that your parameter would then be scaled by the inverse of that, right? It's very important to know that scaling your features does not change the problem, but it can change a lot. At least if you don't have a regularization term, the problem remains exactly the same. You'll have the same loss, the same value at your solution. But it can both make regularization much better and more and better kind of meaningful, much more meaningful, because otherwise you're sort of comparing things with very different size of units. And it can also make things like gradient descent much more reliable and perform much better. Yeah. No, so the question is why are we regularizing? So for now, just say that we are regularizing. I'm going to describe regularization next lecture when we talk about overfitting. That's actually why you want to regularize. It's due to overfitting, to sort of cross-validation errors, things like this, which we haven't talked about at all yet, so don't worry about that yet. I'm putting it here now because when you talk about other machine learning algorithms, you will actually always see them with a regularization term added to it. So I want to sort of emphasize that this is actually what occurs in practice. It's this problem. And that is one reason. And scaling a gradient descent is another reason why you want to do normalization of your features. So these are both sort of forward-looking. The regularization one is forward-looking to next lecture, or lecture 1.5 from now, about about nonlinear methods and about overfitting. And the other reason is about for sort of implementation reasons of gradient descent. OK. And the most common way to normalize, by the way, is to subtract the mean of a feature, where the mean's computed, on all the examples, what's the mean of that feature. So when I say mean of xj here, remember j's index over the different features. So I would take the mean of, say, all the temperatures, subtract that from the temperature, and then divide by the standard deviation of temperatures to get a new number that actually, if you care about it, tends to have mean 0 and standard deviation 1. Is my new kind of tilde xi there. And I do that for all my xi's, except the constant term. You obviously don't have to have a constant term, because that has 0 standard deviation. So you don't do it for the constant term. You do it for everything else, and then you run your algorithm on your new set of weights. After you're done with that, if you want thetas back in the original space, you have to retransform those, and these are the equations for that. And that just ensures, by the way, those equations ensure that theta tilde, which is our one we made on the transformed features, times x tilde, or inner product with x tilde, is equal to this, this transformed theta times our original feature vectors x. Don't worry about why that's the case. Just know that these are the formulas to do that. And also, I'm saying this now because I do this in the notebooks, for example. To make gradient descent work, I have to do this. So that's what these equations are actually doing. Yeah?
For the example of temperature and the peak usage, how much of a difference does normalization make when you do gradient descent on?
It will make a huge difference in that case. You can try it without, actually. Try doing it without in the notebook. It just won't work, because what you have is you have essentially a function that looks like this, where one dimension is extremely scaled like this, and so you end up just bouncing around in your function. OK. Let's talk now very briefly about the implementation of these things. So let's talk about first gradient descent in Python, or sorry, least squares in Python first. So there are libraries that will do all this for you. And in fact, when we talk about next lecture, we're going to talk about some libraries that do this for classification, like scikit-learn. I would recommend that no one do that for linear regression, though. It is literally one line of code. You create your feature vector, which you have to create anyway for scikit-learn, and you type lineage.solve xt.x, xt.y, and you have your parameters out. Right? That is just those equations right there. I would really recommend you do that instead of scikit-learn.classifier, linear regression, and then you don't know what your feature vectors are anymore, and you have some weird opaque interface to it that you don't quite understand. It's fine. You'll understand all those once you go back and have done this once. But even when you understand it, I think this is still easier. Other ones, I can agree that yes, you probably want to just use it for maybe a support vector machine. But that one isn't too hard either. Or maybe boosting, you probably want to do it, use it. For here, don't do that. Just type this. It's really easy. It's one line of code, and it sort of emphasizes what you're actually doing, what you're actually solving here. If you want to add regularization, and I actually won't prove this, but actually, if you have a regularization term there, you just solve this with this being your lambda term plus the identity. And that's actually the solution for the regularized version of least squares. I won't prove that, but that actually falls out from the exact same rules of math and derivative gradients that we had before, and you could try to derive that if you feel like it. So you can solve both the regularized or unregularized version there of least squares. Yeah. I won't derive how it came in. Just trust me, this is the solution if you want to solve least squares error plus lambda. Where here, their lambda is 1e negative 4. Yeah. You can. So if you actually just do that first one, you don't need to. It's pretty stable. So I typically don't when I just run that first one. If you regularize, though, then you should scale them. I think on the, I mean, to a certain point. If you're just doing a tiny bit of regularization just to make it numerically stable, you don't usually need to. But if you're going to have a big regularization, you want to do that. But we haven't talked about why you want to do that yet, though. So let's not worry about that. I think for the homework, you don't have to scale it. You just leave them as they are. Okay, gradient descent is actually equally simple. You start off by initializing theta to be 0. I just have some extra code here, but I compute the gradient and compute the update to theta, and I return theta. Here I'm also returning the loss function as well, the evaluation of the loss function over the iterations here. And the nice thing here is if I want to change from minimizing a squared loss to minimizing absolute loss, I just change 2 lines, or actually even really 1 line of the code. The other line is just to evaluate the function. I change 1 line of code where before that g there is the equation for my gradient, and now g here is the equation for my gradient. So that's the only difference that comes up when you switch from minimizing squared loss to minimizing absolute loss. And finally, if you want some of the code for normalizing features, here it is. This assumes you created an X vector or X matrix that has the all ones term in its last column. What we're doing here is we're basically normalizing all the columns but the last one. So we look at their mean, their standard deviation, subtract their mean, their standard deviation, and add back the ones. Then we run gradient descent on our loss here, and to convert theta back to our original space, we follow essentially the inverse operation, which is just the equations you had on the previous slide. This is a little bit maybe somewhat confusing why these are the equations. That's just these though. And so if you want to figure out why those are the case that they are, look at this condition here and see if you can kind of figure out why that's the case. But don't worry yet. You can also just use them kind of as a formula. Okay. So now we move next to classification. Yeah.
When you did the linear regression on the 2 variables, the temperature and weekday, what did you condition each on? Like, you had 2 plots, right?
Right. So the question was when I had 2 plots. I guess I can go back to it. Or maybe I'll just say it. The 2 plots were showing the case of weekday being 1 and weekday being 0. So I was showing on the x-axis still the temperature, but this one plot was kind of the slice. You can think of it like the slice of that function when it's equal to when the other feature is equal to 1, and the other one's the slice of the function when it's equal to 0. The is weekday feature. I think it's small, but those are they're in the titles of the plots, so you can look back and see the titles of the plots. Okay, let's talk about classification now. So classification, well, I'll give an overview first. So we're going to start classification much like we did with regression by giving an example. In this case, we're going to talk about the challenge of classifying tumors. So this is sort of at this point become a standard machine learning problem, machine learning data set at least, though really was quite a big deal when it was first happening, the fact that we can use machine learning to try to classify whether a tumor is malignant or benign. Then I'm going to give again sort of the more formal review of what classification is in the context that I set up last time of the machine learning notation. We'll talk about a few examples, and then hopefully, again, probably not this time, but we can look at it. We'll talk about some libraries for machine learning. You're going to do some machine learning on the homework, but it's actually going to be different libraries, I believe. Actually, is it? No, are they using scikit-learn logistic regression for the homework, or are they using NLTK? What was that? Using what? In scikit-learn though. Okay, so the code for sort of how you do that will be in here, and we'll cover it. If not this time, then we'll get to it early next time. I'd like to get to today actually. Maybe I'll skip forward to that if we need it. Okay, there's our announcements. We're going over those. Okay, let's take an example of classifying tumors. So classification. All that I mean by that term, all that it means is that we're now predicting, instead of predicting real valued functions, we're predicting discrete valued functions. So things aren't a continuous peak demand. It is this email spam or not? Yes or no? Is this tumor malignant or benign? One of those 2 categories. Is this image of a digit 0, 1, 2, all the way to 9, right? So we were talking about predicting discrete quantities. They can either be binary, and when they are binary, I will refer to them as -1 or +1. Not 0 or 1, importantly. I'll use the convention as -1 or +1. And in multi-class, which we're not going to talk about, but just so you know about it, it's between, say, 1 and k different values. You could also predict that. Let's talk about this example. So this is an example called the breast cancer data set. The idea was doctors would take like a sample of fluid from a tumor. They'd stain it, and then they would look at the cells in this stained fluid. And the question is this tumor, from this view here, malignant or benign? Now, the way they would sort of do that is they would have a person look at these stains and kind of outline a bunch of cells. So there was some manual process here. So the person would actually outline them, and they would use a little bit of image processing to align that outline exactly with the cells. So there was a little bit of sort of computer vision, but for the most part, the fun things, the image processing part, was all kind of manually done. And they would take all these different outlines of cells and compute a few features on these things. So for each cell, they would compute its area, its perimeter, the number of concave portions it had. So if it kind of bends inward at all, that's actually an indication of malignant tumors. And so they would look at the number of times there was a concave point around each cell. And that would essentially give them some features. They would get 10 total features, and then they would also take the worst case features, so the biggest one out of all these cells, the mean over all the cells, and the standard deviation over all the cells to give 30 total features. And that's this sort of canonical breast cancer data set that you actually is included, say, with scikit-learn as an example data set. It was about almost 25 years ago now. And at the time, I think it was actually really compelling application of machine learning to classify. So, a very obviously focusing on a very important medical topic here. So what I'm going to do now is I'm going to look at what this data looks like from the machine learning standpoint. So remember, this is the actual image that leads to the data, but at least back then. Now you could probably actually just use this image directly as input to your algorithm. But at least back then, they couldn't really handle images like this. So what they would do instead is create these features, like I described. And I'm going to look now at a couple of these features and see what this data looks like. So this is the plot, or a plot, of the data. Okay. What I'm showing here is I'm showing two features. So I'm showing the feature of the mean area of these cells. So that's how big are the cells. And I'm showing the mean number of concave points. So if I look across a cell, how many concavities are there in that cell, and what's the mean of that over all the cells? I mean, most of them have no concavities, but some have a few. So the number usually is between 0 and some small amount. The area is the mean area in pixels of the image because they use the same scale, the same magnification factor for all their samples. So this is a view of the data. Now, in color here and symbols, I'm indicating whether or not that tumor is benign or malignant. So as you sort of seems kind of intuitive, maybe, the bigger a tumorous cell is, the more likely it is, in some sense, to be malignant. And the more concavities it has, also the more likely it is to be malignant. But they both carry some additional information, right? So if you have a cell with a large number of concavities, but it's pretty small, it's still probably not malignant. But if you have one that has the same number of concavities, but it's a little bigger, it probably is malignant then. So there's all sorts of these trade-offs, and these two things carry independent information that we might want to use to make our classification. Now, what linear classification is, remember the picture to have in mind when you think of linear regression is drawing a line through the data. The picture to have in mind now is drawing a line that separates these two classes. Okay, that is linear classification. Now it's important to know what this is, and I'll get at this more, but this is not a line fit to the data in any way, right? What this actually is a function that is positive in this region and negative in this region, and which therefore crosses the origin. So crosses not the origin, but it crosses the 0 plane because of the 0 plane, not the origin, at this line here. So in some sense, you should think of the positive examples as being, as actually this plot kind of existing in a 3D space here, where these positive examples are kind of propped out a little bit from the projector, and the negative ones are kind of sunken in, according to the +1, -1 values. And our function is going to be positive where we want to classify it as being +1, the class, and negative where we want to classify it as being -1. Now, I will define this a lot more, but just keep that picture in mind as you think about linear classification. And we'll see this picture again and again, so we'll see it more. Okay, so let's talk now about the formal setting for classification. And fortunately, the nice thing about this is exactly what we had before. So there's almost nothing to say. Just like before, we have input features, which we consider to be vectors in Rn. Okay? Just like before, we have outputs, but the difference now is an output is still in some space y. But the difference now is the output is not real valued. It now actually belongs to the discrete set, either -1 for benign, in this case benign tumor, and +1 for malignant tumor. We have, again, as before, some model parameters theta in Rn. And maybe even more similar to before, we actually have the exact same hypothesis function. So our hypothesis function is just, as it was before, our prediction is just going to be theta transpose x. Now this seems a little bit weird, right? Because this is a real valued quantity. So it's not a discrete quantity, which is what we're trying to predict. This is real valued. And again, this is just, remember, the sum over, I guess I'll use j equals 1 to n, theta j x j. So what this hypothesis function tries to do in classification, in binary classification, is basically what I said before. We want this function to be positive in the regions where yi is positive, is +1. And we want it to be negative in the regions where yi is -1. In other words, what we want is we want to match the signs of our hypothesis with the actual output. So if we're going to make an actual prediction, and I'll note it like this. So if we do want to make a prediction, not just a score, but if we want a prediction, we would just take the sign of that hypothesis function. Okay? Now that's a little bit confusing. That's really actually all that is hopefully confusing about classification. Our hypothesis is actually considered, instead of just our estimate of the actual output, you can think of it like a measure of confidence about how confident we are that this is either +1 or -1. So if we predict, our hypothesis function predicts a very big number, it kind of, informally speaking, means we're very confident that this is in fact a positive example. Whereas if it's small number, we're very, a very large negative number, we're very confident that it's a negative example. If it's right around 0, then we're not that confident either way, or one way or the other. We're sort of unsure about exactly what to predict there. Okay, so it's important to know that what our hypothesis function captures now is not the actual prediction itself. It is actually a measure of confidence. If we want our predictions, we take the sign of this function. And this is going to be important for defining loss functions. This is why I'm writing it this way. And again, now maybe looking at this figure one more time, we can kind of see, remember, the axes here are two input features, right? So the x and y axes here are not x and y in terms of our inputs and outputs. They are, in fact, x1 and x2 are the x and y axes of this figure. And so if you think about sort of the output, that's kind of like the z-axis, right? Where that would sort of be coming out here, and all the positive ones will be raised up, all the ones will be sunken in. And so our function is really a plane in this space that hits the 0 plane in that line is negative in the blue portion and is positive in the red portion. Yes?
So the boundary here like actually has some actual width to it? Because it's all of the points at which you get 0?
So which one was does the boundary have some width to it? So not really, because this is, I mean, it's sort of a, it's a measure 0 set, right? Because this is a continuous linear function, right? So there's only going to be, effectively a 0 set, or it's not a 0 set, but it's, doesn't have any area to that set of where it hits the origin. There's, the hypothesis function, because it's a continuous function, just sort of passes through it instantaneously. It doesn't stay there.
Because there is overlap, that's why we use the regularization term. Is that correct?
Sorry, the question about whether there's overlap. No, those are completely separate, I think. So regularization here has nothing to do with the sort of overlap of the set. Regularization is about keeping the parameter weights small, which is not at all the same as, yeah. So it's, actually, if you can clarify sort of why maybe that point's confusing, I can try to help clear it up, because those are in fact quite separate issues. Actually, yeah. Can you clarify?
As we get, if we have one on the other side, we're sensitive to that line shifting for each one.
Okay, I see. That's the question. So the question was more about like the size of the parameters kind of does govern in some sense the steepness of this function, right? Because if you have very big parameters, you can have kind of a very steep function here. If you have very small parameters, you have kind of a flatter function, and that will then vary a little bit more. So that's true, but that's actually a subtlety that I think is way beyond what I'm emphasizing right now. So if that makes sense, that's great, but that's way more subtle actually than what I'm trying to emphasize right now. You can think of this really like a linear regression kind of problem, just where you have 2 inputs and where your linear function you're approximating is a plane instead of a line. And that plane, you just classify it as opposed to being positive, where that plane is in the positive region and negative otherwise. Now, if I want the equation for that line, this is also important. I see people doing this actually a lot on homeworks, where you have to plot that line. You do not plot some function of this whole thing here, right? What that line actually is that line is the equation that h theta of x equals 0. In other words, that equation for this function says theta 1 x1 plus theta 2 x2 plus theta 3 equals 0. If I wanted to find that line of equation of x1 or x2 in terms of x1, right? This would say this line, the equation of this line is x2 equals negative theta 1 x1 minus theta, or plus theta 3 over theta 2. This is really important. This is the equation of that line, not anything related to the hypothesis function or y or anything like that. Doesn't involve the output of this function. This is the equation for that line, if I'm defining it in the x1, x2 plane. Okay. And if you evaluate your hypothesis, in other words, if I had to plug in, x1, x2 for some region there, it would be a positive number. If I plug it in for some region number here, it'd be a negative number. This is actually sort of conceptually what is the hardest part of classification, because once you sort of see this, then everything else is actually quite easy, because the math is all exactly the same as regression. All right. So now the big question is, I've defined a hypothesis function that outputs real numbers, and my actual labels are -1 and +1. So the question from our standpoint of sort of machine learning are the ingredients we need a hypothesis function. Well, we've called it linear. The second thing we need is a loss function. So how do we define a loss function between real valued hypothesis outputs and -1, +1 values for our true labels? That's the actually other kind of tricky part, maybe, of classification. So the first thing we might try is to just use squared error. After all, -1 and +1, they are categories, true, but they're also just numbers. So let's just use squared loss as we were before. Just call it, the difference is the difference between our hypothesis function and the prediction we make. And this actually works sometimes surprisingly well. This is something called least squares classification. You would think it's a horrible idea, but actually it's not that bad an idea a lot of times. The problem here, I should say the plot I'm showing here is now a different one. Now I have the outputs on the y-axis and only one-dimensional input here. So this is important. This is a different view than my last plots. But consider a data set like this, right? And this actually has to do a lot with those same notions of like robustness to outliers of these functions. If I find a least squares fit, I'll get something like this for my hypothesis function, if I try to fit these points in a least squares sense. But of course, we also know that if I just draw this as my classifier, as my hypothesis function, that achieves perfect accuracy, right? Because it is always negative when these are negative and always positive when those are positive, whereas this one actually gets it wrong. So there's some notion in which for classification, it doesn't matter how far away you are, right? If I predict something really confident, I shouldn't be penalized because I wasn't predicting exactly 1, right? I should be able to predict whatever I want to predict. I can predict 10 if the answer is positive, and I shouldn't be penalized for that. Okay? So that's kind of why we want to think about loss functions other than least squares loss when we talk about classification. So let's give a few examples now. The most obvious loss, and probably the thing that you are wondering why it isn't just from the point, is to say, well, this isn't too hard. What you should be optimizing is how many times you're right? If your sign is positive, so if you predict a positive sign for your hypothesis function, and the answer is +1, that's good. If it's negative and the answer is -1, that's also good, right? So in other words, the loss is 0 if the sign of our prediction is equal to the true value, and it's 1 otherwise, right? So it's essentially, it's just be the number of errors we make if we sum up all of these over a data set. Now it's important that I'm going to write it in a little different way. So I'm going to write this as, I'm going to write that function, which is sort of the very intuitive, it's the thing everyone wants to optimize when we talk about classification. Are you right or wrong in your classification prediction? I'm going to write it like this. I'm going to write it like a 1. This is called an indicator function. So that function is equal to 1 if the inner condition is true. It's equal to 0 otherwise. I'm going to write this function as this, as the indicator of y times the hypothesis being less than or equal to 0. Now, it's important to know that this is the same thing, right? Because if y and our hypothesis both have positive sign, their product will be positive, and so we don't suffer any loss. We suffer loss 0. If they're both negative, it also has positive sign, their product, and so we also suffer loss 0. If one is negative and one is positive, then their product is negative, and so we do suffer loss. We got it wrong, basically. So this is just a sort of an expression for how I write this accuracy. Right? Now, what's important here is this term. This is sort of my key term, and it's the important one. It's the product of the true label times my hypothesis. Because that's also a notion kind of how confident I am, right? Because if I predicted a really negative number and the output is 1, this product would be really negative, right? If it's predicted a high number and this is positive, then it's really positive. So not just the sort of sign, not just the value here, but also sort of how big this quantity is here also has some intuitive meaning, right? The problem, though, is that this loss, which is what we would still like to predict, right? Because we would like just to minimize the number of errors we make in our function. That loss is unfortunately hard to optimize. So I talked a lot about sort of convexity, or at least I mentioned this term convexity, which I'm not going to talk about here much, but just suffice it to say, it turns out that finding the theta, unlike least squares, say, where we could find the theta that really minimized that loss function, right? We could actually find the theta that minimized least squares loss. We cannot do that for 0, 1 loss. The function is what's called non-convex, for those that have heard that term before. And what this also actually means is that it turns out that finding the thetas that would minimize a sum of 0, 1 losses ends up being, in general, an NP-hard problem. So you can't actually do that. Now, because of this, in classification, people have developed a lot of alternative loss functions that kind of get at the same thing. These go by many names, but probably the two most common ones are the logistic loss. Logistic loss is the log of 1 plus the exponent. Oh, I messed up. This should be a negative thing here. I should have a negative sign there. Sorry about that. But that is this green function here. If the product, so if this term here, if this product is positive, log of 1, so this thing will become very, very small. So this will be, again, because it's supposed to be a negative here. So apologies for that. So this exponential of this large thing here will be small. This negative large thing here will be small, and so log of 1 plus a small thing is about equal to 0. So this approaches 0 as you get more and more confident in your prediction. It actually approaches a linear function as to go the other way. So you're taking the log of an exponential, and when this is really big, in other words, when this product is really negative here, this term, essentially the 1 falls out. It doesn't really matter. It plays no role. So this is kind of just like a linearly increasing function there. Right? That's the logistic loss. The hinge loss is kind of even maybe a more direct approximation of the 0, 1 loss. It is just the function that is exactly linear here until it hits the 0 point, and then is 0 from there, and then is 0 from then on. So these look kind of odd, but in some sense they actually capture something very intuitive, right? They capture the fact that the loss in all these cases is bigger the farther we get into the negative region. What that means is, again, remember I talked about this hypothesis, some notion of confidence, and our confidence in a prediction. So as we get more and more confidently wrong, more and more confident, but we are wrong, that's this direction, right? So we suffer, in these cases, for these ones, we suffer more and more loss. So we're sort of penalized more and more if we're wrong for the more confident we are. Similarly, we're often actually sort of penalized less and less, not for this one, because this one actually hits 0 and stays there. But for the other ones, we sort of approach less and less loss the more confident we are in the true answer. And so after that, once we plug in these loss functions, classification is exactly the same as regression. All we are doing is we are optimizing, minimizing some sum of losses on some data set with respect to the parameters. Maybe with regulation there, maybe not. That's all it is. Okay. The only difference now is that loss is defined a little differently, and our hypothesis doesn't directly predict the class. It predicts the kind of confidence in our class label. Now, it turns out most of these things, unlike least squares also, in fact, least squares is kind of its own thing. Nothing else is like it. Unlike least squares, these typically do not have closed form solutions, meaning we actually cannot solve them have in one equation to come up with what theta is. So we have to use gradient descent or some other method. But gradient descent is a perfectly good method for solving them, and it's very, very commonly used in practice. OK, I'm going to say one more thing. I'm going to skip around a little bit, and I'll come back to it, because you are going to use it on your assignment. So I want to mention one thing. OK, so a support vector machine now. Support vector machine, it's a really fancy sounding name. All a support vector machine is it is solving the standard machine learning optimization problem when I use hinge loss. plus the regularization term. That's a support vector machine. The way you solve that is I can write the gradient of this thing. Don't worry about why this is the case here. Basically, our hinge loss looks like this. That's a bad drawing of it. That's all supposed to be 0. This is our y times hypothesis, right? So the gradient of this term here is always -1 here and 0 here, which is sort of actually equal to the negative indicator of whether or not this is less than or equal to 1. And then you sort of apply the chain rule to pick out these two terms in your gradient. Don't worry there. Just know that's the gradient of this function. Really a subgradient, again, because it's not differentiable, but that's the gradient, the subgradient. And you can solve a support vector machine by just iterating that equation. Now, technically, actually, if you want to be really precise, you typically do not regularize the theta on the constant feature. You regularize all the other features. But don't worry about that. We haven't talked about why you do that yet, so I realize it's a little bit odd to talk about that yet. But that's a support vector machine. And if we do this, if we solve it, this is with gradient descent here. I'm solving it. We get this plane. It's actually not quite the one I showed you before. When I showed you before, it was from logistic regression, but they look identical, actually. So we'll just worry about this one for now. These are the numbers. This number, again, this defines this 3D plane. So for this feature, as you increase, our hypothesis gets more positive. That feature, as we increase, it gets more positive, but you subtract a little bit off at the origin, so it crosses the 0 plane at that point there. Everything on the one side is positive, everything on the other side is negative. And before moving on, I'm actually going to show you how to code that. But this next plot shows when I run gradient descent on this function, I get a decreasing loss, as well as I also get a decreasing error. So these are two separate things. So when I talk about loss for a classification algorithm, I mean the actual thing we're optimizing here. That's the hinge loss, right? That's an approximation in some sense to the error, to the 0-1 loss, which maybe is what I really care about. Just how many times am I going to be right or wrong here? But it's one that's much nicer to optimize than the 0-1 loss. Right? 0-1 loss also, by the way, has no gradients anywhere. So it's very, very hard to gradient descent on 0-1 loss, because the gradient is 0 everywhere and infinite right there. So that's not very good. But this is the decrease of loss, and I'm also showing now and it sort of was what you expect, right? As you take more gradient steps, you converge to what here actually is a global optimum. This function's a little bit interesting, though. This function shows now my error over these iterations. So one thing that's very interesting, actually, is that, first of all, if I take literally one gradient step, I already get about 10% error, so 90% accuracy on this problem. And all my other steps, which are decreasing loss so much here, actually just kind of make it a little bit better. I also have a point where I should do better than my final loss here, because 0-1 loss and hinge loss, while they are similar, are actually different loss functions, right? And so there are times, namely right here, where I have some parameters that do better on the 0-1 loss than my final parameters, where my final parameters are those that globally minimize the hinge loss. So these are kind of things to play around with a little bit. It's important, the takeaway here is that when you are evaluating the performance of machine learning algorithms, it is important to always plot both the loss you are optimizing as well as the error you actually care about. And we'll talk about in a second. You actually want to do this on a training set and a test set too, but that's for next lecture. All right, I'm going to skip forward a little bit and talk just briefly about scikit-learn. I'll go through this next time too, but since you have it on your homework, I want to highlight this a little bit. In the minute I have left, but fortunately it's very easy. Scikit-learn is a very common library for Python. It's sort of the most common machine learning library in Python. And the nice thing is it includes implementations of most algorithms like support vector machines. It actually has two versions. One's called a linear support vector classifier, is what the C stands for. So linear SVC and SVC. You can make those actually equivalent by adding the kernel equals linear term to SVC, and the lost equals hinge term to the linear SVC. Now, I want to go on a little bit of a comment here with the no time I have left. And that is that you do have to pay attention when you run scikit-learn libraries to the parameters you are using. Oftentimes, the default parameters that they use for them are not what you actually want to use. And sadly, a lot of data science seems to be driven by whatever default parameters people chose for scikit-learn, because people just run them with the default parameters, which are oftentimes not the best ones. In the case of the support vector machine, the C term there is actually the inverse of the regularization term. So we are actually solving this problem here, where I've taken this lambda here that I used to regularize and actually moved it in front here to be a C term. So if I want very small regularization, that is equivalent to having a very big C term. So I want small regularization here just because I didn't talk about it yet. So why do I want any at all? I don't. So I'm using a very big C term there. But it's important to know what that C actually means. It's the inverse of the regularization term. The other very annoying thing is that I'm also passing a maximum number of iterations you can run for this linear SVC class. The default option there sometimes gives me like 30% error when you get to your solution. I don't know why they pick a smaller one, but it's clearly not enough. And so you have to tune these things. The upshot of this is these require some amount of tuning still. And if you're going to use them, it's great. But here's the code for your own support vector machine. It's 5 lines of Python code, right? It just runs gradient descent on the support vector machine loss, on the hinge loss. So while it's great to have scikit-learn, you should definitely use it once you get familiar with these things. It is my opinion that it is also very important to learn how to implement these algorithms and what they are doing so that you can actually use the algorithms effectively. Because if you just use the default options with C equals 1, say, it would not be what you wanted here. It would not give you the answer you want. And with the max iters being much smaller, it would not give you the answer you want. And you wouldn't, you'd think a support vector machine couldn't solve this problem when in fact it can solve it. So just be aware of that. This is just gradient descent on it. It's the exact same procedures I wrote for least squares, just with this loss for the support vector machine. Know that that is something you should do, at least for this level of algorithm. I think in 688, you will have to do that for some of your homeworks, but for 388, you won't. But that's all I'll say for now, because I'm a few minutes over anyway. So see everyone. And this is all you need for your homework. But see everyone next Monday.